Welcome to EE331 Lesson 21. We're going to touch on AC source transformation, where we'll see again that the AC form is very similar to the DC version of that concept. The new concept that we're going to learn today is superposition. First, let's start with source transformation. Source transformation in AC is of the same format as in DC. We take a voltage source that is in series, this time with an impedance, and we can convert that into a current source that is in parallel with an impedance between the same two terminals. The impedance will be of the same value, and the current source will have a value Is that must obey the equation Vs equals Is times Z. Again, this looks very similar to Ohm's law, but it is not Ohm's law. Source transformation also works the other way. That is, you can go from a current source back to a voltage source. All the same restrictions apply in AC as they do in DC. You shouldn't transform the parameter you are looking for, or a parameter upon which a dependent source depends. AC source transformation may be your preferred tool because AC nodal analysis can be very tedious without System Solver. In this practice problem, we're going to calculate this current Ix that goes through the 0.1 farad capacitor. We're going to do so using source transformation. Because this is an AC problem, we need to make sure that everything is in terms of phasors or impedances. We can see that we have time domain expressions for the source, and we have henries here and farads, so we need to do some conversions. First, let's convert the source into phasor. We can write this source as a phasor voltage of value 20 angle 0 degrees volts. Noting that the source has a frequency where omega equals 4 radians per second, I can calculate ZL1 for the 1 Henry inductor. ZL1 is going to be plus J times omega times L1, which is plus J times the 4 radians per second times the 1 Henry. That's plus J 4 ohms. I can similarly calculate ZL2 for the 0.5 Henry inductor, which will be plus J times omega times L2, which is plus J times the 4 radians per second times 0.5. That comes out to plus J2 ohms. For the capacitor, we need to calculate ZC. ZC is going to be equal to negative J divided by omega times C, and that's going to be negative J divided by 4 radians per second times the 0.1 farads. That equals negative J 2.5 ohms. Formally, we would also be representing the current Ix as a phasor, and the dependent current source here would be 2 times the phasor value of Ix. Now that everything is in terms of phasors and impedances, let's start doing some source transforms. We can see that we have two candidates, and we'll end up doing source transforms on both. The first candidate will be the current source that is in parallel with this plus J2 ohm inductor. We can do a source transform even with a dependent source. We just can't transform what we depend on, which is Ix. So we're not going to touch the capacitor throughout this problem. Doing that source transform leaves everything else intact. But now I put the impedance of the J2 in series, and I draw a dependent voltage source with the plus pointed up because the arrow was pointed up in the current source, and I find the value of that voltage source as 2Ix times the plus J2 ohms. That can be simplified to plus J4Ix. In the next step, I'm actually going to do two simplifications. First, I'm going to combine these two inductive impedances in series. Second, I'm going to perform a source transform on these two components. Doing the source transform, I get a current source that will be in parallel with the 10 ohm resistor. The value of the current source will be 20 angle 0 degrees volts divided by the 10 ohms. That equals 2 angle 0 degrees amps. The capacitor is still untouched, so it still sits here as negative J 2.5 ohms. And now the inductive impedances are combined in series for a combined plus J 6 ohms. The dependent voltage source still sits out here to the right. Remember our objective, Ix, still flows through that capacitor. The next step is to do one more source transform. I'm going to do that on the right side of the circuit. Doing that source transform obtains a dependent current source with the arrow pointed up because the plus was pointed up, and I flip the plus J6 inductor down into parallel so that it's plus J6 ohms like so. The value of the new current source will be plus J4Ix divided by plus J6 ohms. That obtains a value of 2/3 Ix without any J's. Completing the rest of the circuit, I still have the capacitor and the 10 ohm resistor and the independent current source. At this point, the circuit is entirely in parallel. I can start doing some combinations here as well. Let's combine the two current sources together. Combining the current sources results in a combined current source, like so, that is in parallel with the 10 ohm resistor, the minus J 2.5 ohm capacitor, and the plus J 6 ohm inductor. The value of this combined source is just the sum of the two current sources, since they both point into the upper node. That's going to be 2 angle 0 degrees plus 2/3 Ix. Remember that I'm still searching for Ix, which is the current through the minus J 2.5 ohm capacitor. I can further simplify the problem by making the parallel combination of the 10 ohm and the J6. Notice that I don't include the minus J 2.5 ohm in this because I don't want to touch what the dependent source depends upon. Doing 10 ohms in parallel with plus J6 ohms correctly yields 5.145 angle 59.04 degrees ohms. The resulting circuit would look like so. At this point, I'm ready to do a current divider rule equation for Ix. The current divider rule would say that Ix is equal to 2 angle 0 degrees amps plus 2/3 Ix, the total current, times a fraction. And that fraction would have on top ZEQ total parallel, and on the bottom I would have the minus J 2.5 ohms, which Ix flows through. ZEQ total parallel, which is the parallel combination of the 5.145 angle 59.04 degrees ohms and the minus J 2.5 ohms, is equal to 3.94 angle minus 66.8 degrees ohms. Substituting that value back in for ZEQ total parallel, I obtain an equation where I can solve for Ix. It's a little bit more work since Ix is on both sides of the equation, but if you do the algebra right, you'll get that Ix is equal to 7.59 angle 108.4 degrees amps. Notice in this problem they asked for Ix, they probably could have clarified that it's Ix of t. If I want this in the time domain, I can simply represent it as Ix of t equals 7.59 cosine 4t plus 108.4 degrees amps. The real new content in this lesson is actually superposition. Superposition is a technique applicable to all linear circuits. This includes both the DC and AC circuits that we have studied so far, because we've only included resistors, inductors, and capacitors, which in their ideal form are all linear. So far we did not need superposition, but we could have applied it even in the DC problems. You only really need superposition when we're dealing with circuits that have more than one frequency. Superposition is based on the principle that linear systems produce outputs that are proportional to their inputs. As a result of this principle, the outputs of individual inputs can be summed to produce the total output. This includes inputs that have different frequencies. Take, for example, this circuit here, which has multiple frequencies. We can see that in the fact that we have a 10 cosine 2t voltage source here, a DC voltage source here, and a 2 sine 5t current source here. When faced with an example like this, where we have multiple frequencies and we're looking for a parameter like V0 of t, the solution is to follow the superposition procedure. The first step in the procedure is to count the number of frequencies in the circuit. In this case, from the 10 cosine 2t, we have 2 radians per second. From the 2 sine 5t, we have 5 radians per second. And from the DC source, we actually have a DC frequency, or omega equals 0. The second step here is to redraw a circuit for each of those frequencies. Now there are some sub-steps to doing each of these drawings for each of the different frequencies. First, we need to turn the sources that are not at that frequency to 0. That is, we need to kill those sources just like we would when doing the Thevenin procedure. For the omega equals 2 radians per second circuit, that would look like this. You see that I've kept, in phasor form, the 10 angle 0 degrees volts, but I have made the current source an open and the other DC voltage source a short. This is because those sources are not at 2 radians per second. The next step is to turn all elements into impedances or sources to phasors. We can see in this case that the source is already a phasor and that I've already done the calculation where the inductor is j omega L, and therefore J4 ohms at 2 radians per second, and the capacitor is negative J divided by omega C, which is negative J5 ohms in this case. The reason we highlight that you need to recalculate the impedance and the phasors for each frequency in the circuit is that the circuit will look different at each frequency. Consider the omega equals 5 radians per second circuit. Here I've not only changed the source that is active, I've killed the voltage source on the left and the voltage source on the right and kept the current source. The current source now has a phasor value that is just 2 angle minus 90 degrees amps. It's minus 90 degrees because the current source was a sine wave. You'll notice here that I don't have to do anything to take account for the fact that omega equals 5 now with regards to the source. That's because the frequency is implied in this representation of the circuit. To be consistent with that representation, where omega equals 5, I have to recalculate the impedances. That is, the inductive impedance is still j omega L, but now omega is 5, so when I calculate that, it comes out to j10 ohms. Notice how that's different than the j4 ohms when omega equals 2 radians per second. I do the same thing for the capacitor, where this time the capacitor's impedance is minus j2 ohms instead of minus j5 ohms. For the DC circuit, we do the exact same thing, but we operate at a frequency of 0 radians per second. We still kill the sources that are not at DC, so I short the voltage source, and I open the current source. And with DC, I can also remember what inductors and capacitors are at steady state DC. Inductors become shorts, and capacitors become opens. The resistors stay the same, and I draw my DC source. Now in each drawing, it's important that I annotate the parameter of interest within that drawing. That is, I will draw V0 C over here in the DC circuit. Notice that there's a V0 B and a V0 A in the other two circuits. This is because each circuit represents a subpart of the total answer. For the AC circuits, I need to solve in phasor form. That is, for omega equals 2 radians per second and omega equals 5 radians per second, I need to be calculating V0 A as a phasor and V0 B as a phasor. This notation really isn't necessary for DC since there's no need for phasors at DC. At this point, I apply my AC or my DC circuit analysis techniques on each of the individual circuits in turn to solve for the parameter of interest, so V0 A, V0 B, or V0 C. The next step is to take each of those three subpart answers and convert them into the time domain. That is, if I had the phasor representations, such as V0 A and V0 B, I need to get V0 A of t and V0 B of t. Again, with DC, there's no conversion necessary. The conversion back to the time domain is important because the total combined answer for a regular old V0 of t requires that to be in the time domain. Specifically, I cannot add phasors that are of different frequencies. So the last step is I sum up the time solutions for each of the three circuits. That is, I take V0 A of t plus V0 B of t plus V0 C of t, which will just be a constant value, and that will equal V0 of t total. And that will be my final answer. Superposition problems will test your understanding that impedance is frequency dependent and give us many opportunities to practice our circuit analysis techniques, both in AC and in DC. In this practice problem, we're going to find V0 in the circuit below by superposition. We're forced to use superposition in this case because I have two sources with two different frequencies. The current source is at 10 radians per second and the voltage source is at 5 radians per second. I need a circuit drawing at each frequency. At omega equals 5 radians per second, the drawing is like so. Notice that I've opened the current source that is not at 5 radians per second. For the voltage source, I can put that in phasor form as 75 angle minus 90 degrees volts. The minus 90 degrees comes from the conversion from the sine to the cosine base. The 8 ohm resistor is the same, but ZC and ZL need to be calculated for this specific frequency. We can calculate ZL as equal to plus J omega L, which is plus J times 5 times the 1 Henry, which is just J5 ohms. ZC is calculated as negative J over omega C, which is minus J divided by 5 times 0.2 farads. That comes out to minus J1 ohm. The target in this circuit is what I'll call V0 A. the voltage across the capacitor. I can now use any circuit analysis technique that applies to this frequency domain representation to solve for V0A. I'm going to simplify the circuit by combining these in parallel, and the parallel combination of negative J1 ohm and J5 ohms equals negative J1.25 ohms. The resulting circuit looks like so, where V0A is like so, across the minus J1.25 ohms. This is a perfect setup for voltage divider rule, so I calculate by the voltage divider rule that V0A is equal to the 75 angle minus 90 degrees volts times the minus J1.25 ohms divided by the 8 minus J1.25 ohms. Doing that correctly yields V0A as a phasor equals 11.58 angle minus 171.11 degrees volts. I know eventually I need that in the time domain, so let's go ahead and do that conversion. So I get V0A of t equals 11.58 cosine 5t minus 171.11 degrees volts. The other frequency in the circuit is when omega equals 10 radians per second. I have to start over now and do another drawing. Notice that in this drawing I've shorted the voltage source that is not at 10 radians per second, and I'm going to write in phasor form the current source as 6 angle 0 degrees amps. The 8 ohms is the same, but I have to recalculate ZL and ZC because I'm at a different frequency now. ZL equals plus J omega L, which equals plus J10 times the 1 Henry, which equals J10 ohms. ZC is equal to minus J over omega C, which is minus J divided by 10 times the 0.2 farads, and that obtains an impedance of minus J 0.5 ohms. Notice that these values are different than the omega equals 5 radians per second circuit. My target in this circuit is what I'll call V0B. It's the voltage across the capacitor. At this stage, we can use any circuit analysis technique we want, and if we look carefully, we can see that the 8 ohm, the minus J 0.5 ohm, and the J10 ohm are all in parallel. So let's combine them together. Doing so will still preserve the two nodes that V0B is across. Doing the parallel combination correctly yields 0.5252 angle minus 86.24 degrees ohms. The resulting circuit looks like so, where V0B is across that single impedance. We can calculate V0B simply by Ohm's law, where we take the current through that impedance, 6 amps, times the 0.5252 angle minus 86.24 degrees ohms. Doing that correctly yields the phasor value of V0B is equal to 3.15 angle minus 86.24 degrees volts. I need to convert that to the time domain, that is, get V0B of t, which will equal 3.15 cosine 10t minus 86.24 degrees volts. The final step here is to combine my two time domain expressions. I must combine them in the time domain. I'll obtain that V0 of t is equal to V0A of t plus V0B of t. The simplest way that can be represented is simply 11.58 cosine 5t minus 171.11 degrees volts plus the 3.15 cosine 10t minus 86.24 degrees volts. And that's it. There's no further simplification required. You'll basically have a term for each frequency in the circuit. In this practice problem, we're going to look at a real-life circuit topology known as a bias T. The purpose of the circuit is to allow combined AC and DC signals to pass to the output in a specific way. In the case of the circuit below, we want to apply a 4 volts peak-to-peak 2.45 gigahertz signal and a 5 volt DC signal simultaneously across the load resistor, or load. However, the amplifier that provides the 2.45 GHz signal also has an undesired 10 volts DC offset. We can see that from the series voltage sources here. The bias T will help us to block that undesired 10 volts DC, pass the RF signal, and pass a desired 5 volts DC that comes from some other source. We're asked to calculate the voltage across our load as a function of time. I'll draw that like so, and call it V load. I need to use superposition in this problem because I've got two different frequencies, DC and the 2.45 gigahertz. First, let's start with the DC circuit. At DC, I'll draw a circuit where I've shorted out the 2.45 gigahertz voltage source. That's because it's not at DC. I keep the 10 volts DC source and the 5 volt DC source. Remember that a capacitor at DC becomes an open, and that an inductor at DC becomes like a short. The resistor will stay the same, and we are looking for the voltage across that resistor, or at least the partial answer, which is V load A. If we look at this circuit, the fact that the capacitor acts like an open at DC and that the inductor acts like a short means that the 10 volt source is not connected at all to the 50 ohm load, and that the 5 volt DC source is directly connected in parallel with that 50 ohms. Therefore, we can say that V load A is simply 5 volts DC. We get a different circuit at the 2.45 gigahertz frequency. In that circuit, I keep my 2.45 gigahertz source and I make shorts of my DC sources. The 2.45 gigahertz source can become a phasor, 2 angles 0 degrees volts, and then I'll have a capacitive impedance and an inductive impedance at that frequency. The resistor again will stay the same at 50 ohms. The target in this subcircuit is V load B. I need to calculate the impedance ZC in this circuit. ZC, which is minus J over 2 pi FC, is minus J over 2 pi 2.45 gigahertz times C, which is 100 microfarads. If you do that correctly, you'll find that that is minus J 649.6 nanoohms. Yes, it really is that small. In fact, this is very intentional. For ZL, we will calculate that as plus J omega L, which is plus J 2 pi FL, which is the plus J 2 pi 2.45 gigahertz times the 1 Henry. That gets me a value of plus J 15.39 gigaohms. Yes, that's correct, gigaohms. You can see by comparing these two values, the J 15.39 gigaohms versus the minus J 649.6 nanoohms, that the nanoohms basically is nothing compared to the plus J 15.39 gigaohms. This is intentional as well. In order to solve for V load B, let's combine the inductive impedance with the 50 ohm resistor in parallel. Doing so results in a circuit representation like so. The combined parallel impedance of J 15.39 gigaohms in parallel with 50 ohms is equal to 50 angle 0.00000 something degrees ohms. The point of the matter is that if I take 50 ohms in parallel with something that has such a huge impedance, that it will essentially just be 50 ohms, which is essentially its original value. If I were to do a voltage divider rule on this circuit, where I take V load B is equal to 2 angle 0 degrees volts times 50 ohms over 50 minus J 649.6 nanoohms, then I'll obtain that V load B is essentially just 2 angle 0 degrees volts. 50 ohms is much larger than the contribution of the 649.6 nanoohms. That is, we essentially pass all of the AC RF signal to the output, which was our desired goal. In the time domain, that is, V load B of t equals 2 cosine 2 pi 2.45 gigahertz times t plus 0 degrees volts. To complete the problem, I need to take my answers from V load A and V load B and combine them together in the time domain. In the time domain, V load of t is equal to 5 volts DC plus 2 cosine 2 pi 2.45 gigahertz times t plus 0 degrees volts. That was exactly what we wanted to accomplish with the bias T. We got the 5 volts DC offset. We did not get the 10 volts DC offset, but we did get pretty much the entirety of the RF signal. We were able to do this because of the superposition principle and the tactical use of the capacitor and the inductor, specifically with the DC circuit. The capacitor blocked the DC voltage. This is why capacitors are sometimes referred to as DC blocks. In the AC circuit, even though the 5 volts DC source becomes a short, the 1 Henry inductor became an impedance that was so large that it basically blocked any of the RF from going down it and channeled it down the 50 ohm resistor. This is why inductors are sometimes called RF chokes, because they don't allow the RF through them.